I am going to click the record button. At the end, there will eventually be I will share it with people who are interested. Next, I need to share my screen. Can anyone see my screen?
Yes.
Okay, then I'm just going to continue. Thank you, Robbie. Thank you all for coming. So a while back, Okazaki presented a very nice algorithm for balancing red-black trees. Basically, anytime you insert a node into a red-black tree, you end up with one of the 4 types of trees here shown on the sides. And if you then, depending on which tree you have, you rewrite it as the center tree, you get a nice balanced tree. The problem with this algorithm is, although it looks really nice when you draw it on paper like this, this is the actual code for that algorithm. It looks like this because, unfortunately, when you are programming on a computer, right, we generally have to take the concept we're programming and translate it to text. Now, if we take a step back, right, and we think about what a program should be, right? A program really should be a thing that we communicate to people, not to computers. And if the thing we're presenting to people is like that diagram we drew earlier, well, ideally, what we put in a program should also be like that diagram. More specifically, it should be a diagram that is very specific to the problem we are trying to solve, in this case, tree balancing. So to work around this, programmers tend to write tree balancing code that looks kind of like this. They have the nice pictorial representation in a comment above the function, and then they have the function that actually does the tree balancing below. Now, this is seemingly good, except it has a few problems. First, you're limited to the types of pictures you can draw in ASCII, which is a fair amount, but it's not, it's still fairly static. But the bigger problem is the comment, despite being the thing people read, is not actually the code, which means it's very easy to actually get the comment out of sync with the code. So we really do want to be able to put non-textual elements in the code as well as not just the comments. So a first attempt at this was a programming, this wasn't the first, but a first attempt one could try is something like Scratch, which is an entirely visual programming language, but that you can use. In the case of Scratch, it's actually used for pedagogy, and it works very well in that domain. Except the problem is when you try to bring this to other domains, you very easily end up with something that looks like this. This is the Unreal Engine Blueprints feature, which is a sort of visual programming language for generally first-person interactive world things. And I don't know about you, but I personally think this is a mess. Now, this isn't inherent to blueprints. You can make good ones, but it's very easy to make things that look like this. So we do actually want text. We don't want just visuals, right? We want a mix. we want to use text where appropriate and visuals where appropriate. So another attempt is something like snips in the Dr. Racket IDE. This works reasonably well. It allows us to actually embed images right within our code. The problem is it's tied specifically to Dr. Racket. And if you try to open up this code in anything but Dr. Racket, you end up with this. Not only does this not look at all like the program we had, but if we scroll down even further, you end up getting stuff like this, which is just a completely unreadable mess right in our code. So we want something that's not just tied to an IDE or not just a plugin to an IDE, but we want something that's going to work potentially in other IDEs. Maybe you don't get the picture, but you can at least read the program. And we want it to be linguistic so that so that people can make new extensions. What we want is something like heterogeneous visual languages. Now, there's been a lot of attempts at things like this, and they've all fallen short for this particular goal in one of many ways. Like either, despite being linguistic, it still assumes you have an IDE, and so anytime you open it up in a text editor, you get a completely different looking file. It is textual and as well as visual and can be opened in a plain text file, but it's in another language that's not really used by anyone and thus doesn't really get any adoption. To things like, say, Sketch and Sketch, which is really great at the one domain it's designed for, but is not really is not really meant to enable people to create programs for new types of domains. To things that are actually VM based, but so not actually a programming language, to things that are actually REPLs instead of, again, programming language like. And to be clear, all of these are really good projects, but none of them quite fit the mark that we're looking for here, right? Which is, we want to mix textual and visual programs. We want it to be part of the programming language, not just sort of a REPL interaction or a VM interaction. And we want it to work for at least some definition of work, in any IDE or plain text editor we would potentially write the code in. And we would want it to work with an existing programming language, if at all possible. So what we would want is something like this here. This is a the balance tree algorithm with the 4 pattern trees and the resulting template tree, all written within actual code. And this is what it looks like in the Dr. Racket IDE. What we want is what we call visual and interactive syntax. Okay. So the question then is it possible to create a mechanism for creating and using visual and interactive syntax that is both useful and usable? All right. That means to prove this thesis, or not prove, to defend this thesis, we need 2 components. We need to show that interactive syntax is useful, and we need to show that interactive syntax is usable. All right. Now, for the most part, these definitions, useful and usable, are the pedestrian meanings of useful and usable. Something is useful if you can use it. Something is usable if it's something is useful if there's a good use for it. Something is usable if you can use it. But there's one other component here. For for something to be useful, not only does there need to be a use for it, but programmers have to be able to use this to actually design new types of extensions, right? We're not just trying to make a thing for a particular domain. We're trying to make a thing that can be extended to any type of domain a user may encounter. Now, with that in mind, something is usable if you can actually realize this design and use this design in programs. So I've mentioned that we want this to work in any particular domain. The question then is, well, what kind of domains are we talking about? I showed you tree algorithms, but some other ones, so matrix operations, it could be linear algebra, but it could also just be tables or spreadsheets. Like you see this kind of desire a lot in financial software, as well as, say, databases such as, or visual sort of databases like Microsoft Access. Say if you're implementing a file system, you might want to have a visual representation of the internal data structures, such as, say, inodes, that you can then write your various file system algorithms, in terms of that graphical representation. You may want something like a graphical binding construct. So that's if you have a variable in your program that's not a name or a piece of text, but is actually, like, say, a picture. At first glance, this seems sort of silly, but you actually do see this sort of thing in parametric CAD software, where you want to bind a component to a certain set of parameters, and you'd like to be able to refer to the component as the component and not just a name that represents the component, because you want to place it in somewhere in a three-dimensional space. I made a video editor that's a programming language for editing videos, but you may want to actually put graphical video editors right within your code. So interactive syntax might be used for that. Same with circuit simulators. While you're designing, like, say, a CPU, you may want to test various digital and analog properties of that CPU while you're developing it. So, and you may want to lay the thing out graphically. And form builders is interesting, right? So the domain of creating new types of syntax extensions is in and of itself also a domain. So you may want to have a graphical piece of syntax for defining new types of graphical piece of syntaxes. In this case, maybe your form is a piece of graphical syntax, and you may want to design your form graphically. So that's a sort of meta interactive syntax extension that would be nice. And finally, this one may seem silly compared to the rest. Consider board games. Now, imagine after building board games, or before, you want to write unit tests for these board games. This is what really shows the power of this generic visual and interactive syntax mechanism over a system that only handles a few primitives. Because no matter how robust your primitive is going to be, it's not going to come with a syntax extension to help you build unit tests for a game called Suro. All right. Now, if you've never heard of Suro, you would be forgiven. It's not a super common game. Basically, the way it works is you have several players. They put tokens on the edge of the board, and in succession, each player puts a piece, like a tile down, that has paths that moves their token along the path. Stuck with their token following the longest path at the wins. Now, to build unit tests for this, my internet, just 1 second, Elizabeth, is my connection still strong? Okay.
You're
I
fine.
apologize. Zoom was telling me my connection was spotty. All right. So building, thank you, Matthias. So if you were building a unit test for this in a pedestrian-ish language, pedestrian meaning purely textual in this context, it's going to end up looking like this. Now, you may be thinking, I picked out a really ugly representation, and this was actually several people, including myself and my advisor and a few others, did their best to try to come up with cleaner representations. And nothing was substantially cleaner than this. They had some properties that were nicer, some that were messier, but they all did not communicate the essence of what it is we're trying to test here, right? So to show you what it is we're going to try to be testing, we have two extensions. The first is a tile extension that allows programmers to make new path components and connect up a tile. And then a board extension that allows programmers to put these tiles on the Suro board. Now, with these two extensions, we can rewrite this unit test as this here, right? In this unit test, we have a board and we say player 0 is placing down a tile, and we end up with the new board on the right. To me, this is clearly cleaner than the textual representation. So this is nice. The question is, how do we realize it? Well, for this example, we're going to be using Racket as a base. We're going to be extending Racket with interactive syntax support. So we're going to call this Racket Visor. And what I'm going to propose is we're going to use Dr. Racket as a base for presenting these extensions. Now, again, this is just text. You can use the system in any text editor. It's just that Dr. Racket will be the one with the nicest presentation. So before we begin building our interactive syntax extension, we want to start by thinking about what is code, or rather, when does code run? When you make a program and you just put some code in it, we call that runtime code because this is code that is running when you run your program. Sometimes people think of this as a fancy language feature, but almost every language has an ability to insert some compile time code intermixed with your runtime code. That's code used generally by the compiler, but it's just run at when your code is compiling. Frequently, it's to tell the compiler instructions on how to compile the code. What makes interactive syntax special is it introduces a third type of code, edit time code. This is code that runs as you edit your program. So if we had this program here opened up in a text editor that knew to run edit time code, it would just be printing out the word editing repeatedly as you're editing your code. Okay, so with that in mind, this is what an interactive syntax extension looks like on its own. In this case, because we're basing it off of Racket, we're going to be mirroring the Racket GUI system, which is object-oriented in nature. We're going to be building the Suro tile extension. And the base here is just simply the base interactive syntax extension the tile is based on. The first ingredient in any interactive syntax extension is state. This is just the stuff that is going to be used to present your interactive syntax extension by things, say, the view. You could think of the view as a function from state to picture. It's also used by an event handler, which you can think of as a function from state to some event to the new state. These three things combined generally, follows the model view controller pattern, with your state being your model. What makes interactive syntax special is this fourth thing, your code generator. This is a function that takes state and produces a piece of syntax used in your programming language. So when we go back to thinking about phases, all right, this view and this event handler, they run at edit time. They run as you're writing your program. This code generator runs when you're compiling your program. Now the state, and also I should mention, it's running specifically to generate runtime code. So the return value of the code generator is itself runtime code. Now, the state is interesting because it exists at both compile time and edit time. This is essentially the bridge between compile and edit time, as it's needed for compile time to determine what the what syntax turns into. What the state turns into syntax, and at edit time to determine what the state turns into the events that get handled. To add interactive syntax extensions to code, you use sort of an IDE gesture. In this case, you click a button and it pops up a dialog box, and you enter the module the extension's from and its name. And fast forwarding this animation a little bit, you end up with basically something like this here. This is the actual red-black tree we saw earlier, and it's going to be used to balance this tree here, which you can see when we run it is balanced. So it is important to remember, though, if we think of this example, it is still text. So if we're to open this example in something that is not Dr. Racket, it ends up looking like this. This is admittedly not as nice as that picture, but it is still very readable. It is the actual textual representation or presentation, if you will, of that tree. Any text editor that can handle pictures and can run Racket code, however, will still show us this tree. So there we go. Users can use this mechanism. There's clearly useful use cases, and they can make new types of extensions. The question is, can they actually use this? And unfortunately, the answer is no. It's just simply infeasible to use. Why, though, did it fail? So there's three components in terms of usefulness and usability. First, we want the ability to mix text and interactive syntax. We got that. It needs to be IDE agnostic. We got that. And finally, we need to be able to reuse the GUI. This means two things. First, we need to be able to use the same GUI code in our application as we do in our unit tests. And Racket, unfortunately, fails at that because Racket uses, the Racket's GUI is stratified. You can have operating system widgets, and you can have code editors, and you can put the code editors in the operating system widgets, but not the other way around. That's a huge problem, and it means that to use interactive syntax, we had to make a custom interactive syntax specific GUI. And the thing is, making a GUI that is on par with other GUI frameworks that have had literally decades and teams of experience, teams of people developing it, it's completely impractical. So as a result, it's just really slow and clunky to use. So that's it. We're done. I should go back and spend 4 more years, right? It's not usable. Well, there is fortunately one thing we can use to the rescue. It's the document object model. This is the same thing that is based in the web browser, or the same thing that powers the web browser, which is designed specifically to handle mixed textual visual content. I mean, for heaven's sake, this slideshow we've been watching has been done entirely in the browser. And perhaps when you're done, you might go with this talk, you might go and watch, say, a YouTube video also in the browser while playing some silly little web game in the browser and catching your latest news article also in the browser. Needless to say, the DOM can do a good job handling mixed content. It has had literally decades of teams creating hundreds of human years of experience, developing it. It can actually run several different languages, stuff like JavaScript, ClojureScript, TypeScript. WebAssembly even allows languages like C to a certain extent to run in web browsers. It's portable. It runs on any computer pretty much ever. So it doesn't have as strong a notion of phasing, but it definitely has the ability to develop code and run code right all within the browser, all at the same time. And it, very importantly, it cares a lot about sandboxing. It wants to make sure users are protected from malicious web pages. So we're going to use the browser to save the day here. And Racket currently does not run in the browser. So we're going to actually switch from Racket to using ClojureScript. It is also a list like Racket. It is extensible like Racket. So it checks all of the boxes, right? Well, there are some downsides, mostly inherited from ClojureScript. ClojureScript requires its macros to be run in a separate file from the file it's defined in. So that definitely is a drawback. Because of the phasing being ad hoc, the sandboxes, while the user is protected, the IDE not so much. And actually, there's one other big downside. It's Clojure's macro system is completely unhygienic. Some of you may not care. Some of you absolutely care. But it is either way a very major downside. So this prototype for ClojureScript is going to follow the ClojureScript convention of putting core in the front of things. So we're going to say this thing is called core.visor. Now this is a language, so we're also going to bundle it with a IDE called Allied. This is just a general ClojureScript IDE, but we're going to add interactive syntax extensions to it. Actually, we're going to make the whole Allied IDE as well. This is the architecture for the Allied IDE. It's a fairly pedestrian IDE. You've got just the text editor that you write code in. It stores all the files for that IDE locally on the user's computer. But what's interesting about Allied is it can actually embed React, for people who don't know, is a library for creating just sort of web components. It's made by Facebook, actually. Is one of the most common browser graphical libraries there is. And so using this IDE, we can take ClojureScript and run code in the file, or run the stored ClojureScript code. And what we're going to do is pass it to a piece of software. Well, first we're going to pass it to a ClojureScript compiler, which will compile it to JavaScript, and then pass that JavaScript to another piece of software called Stopify. Stopify serves two main purposes, okay? The first thing it does is it creates a virtual sort of DOM environment to run the code in. That way, when the code runs, it doesn't mess up the DOM environment that the IDE itself is running in. The other thing it does is it allows you to have useful IDE features for your code, such as pausing or step-by-step debugging. Now, what makes Allied here interesting is there's a second path. This is the interactive syntax path, and it takes code from your current editor. It passes it through that same ClojureScript compiler, Stopify evaluator pipeline, but instead of running the code directly, it sends it back to the Allied IDE as React components that can be embedded right within your code. Now, going back to the definition of our Suro tile widget, we can see that it actually is going to follow the same sort of pattern that the Racket variant followed. There are some differences, mostly because while the Racket prototype followed the Racket way of programming, ClojureScript Core Visor and Allied tried to parody the Clojure way of programming. So the first thing we do is we have our view and our event handler. They're both bundled together into one function, which is a thing that happens frequently on the web. And we also have a second function for code generation. You may notice that there is no actual state. Well, that's because in Core Visor, the state is actually passed directly to the view and event handler, as well as the code generator. And the view and event handler is actually responsible for detecting if the state has not yet been initialized and initializing it. All right, so with all this in mind, what does our interactive syntax extension look like? Well, it looks something like this. All right, so we can open, when we insert it in, we have this button, we can open and close it, and we have a tile here, and we've got paths, and this is basically like the unit test we had before. We want to see if we look up this path to see what B is connected to. We want to see, is it connected to G? Well, as you can see here, when we look at this, B is actually connected to F, not G. So when we run this, we expect to see an error printed to the console saying that, no, this fails, F is not equal to G. But if we were to change G to F and then rerun it, we'll see that the console is actually completely empty. Oh, there we go. Now, this is still even though it's drawn pictorially, it is still just text. And we can see the textual representation of the IDE here. And actually, if we go and turn off visual editors entirely and just go look at what the file looks like, we can see this is what happens if we open this file up in something like Emacs or Vim. Finally, because this is still just text, if we go and turn interactive syntax extensions back on, we still get all of the nice properties we would want from editing text. So we can still just copy and paste this, and we can even go and open up a new file and put it in here, and we still get the proper interactive syntax extension. Of course, if we run it in here, we're going to now get an error because we didn't include any of the require statements to give this any runtime meaning. Cool. So we made this prototype. It's just as useful as the previous one, except and it clearly seems to be usable. At least the previous one was so unusable it didn't get to the point where we had essentially anyone but me try it. This one is good enough. I used it. I'm happy with it. I had a few of my friends use it. They were happy with it. So now, how do we show, besides just a small amount of anecdotal evidence, that this is actually usable? Well, what we're going to do is we're going to actually do some user studies on it. Let's break down usability into 3 particular components. The first component is code comprehension. This is, can programmers read code with interactive syntax extensions? The second one is, can programmers write code that is using interactive syntax extensions, both the code around the extension as well as updating the extension itself, the code in the extension. And finally, can they actually use this library to create new types of interactive syntax extensions? Now, to best test this out, we're going to actually split these 3 aspects into 2 separate evaluations, okay? We're going to use one evaluation for comprehension and use, and a second evaluation for interactive syntax creation. The reason we're doing this is because the first type is not going to take that much time. It generally is going to take less than an hour to see if someone can read code and write a little bit of code around an extension, or write a little bit of code in an extension. Because of this, we got 30 different participants, and we gave them essentially 2 programming scenarios and asked them a series of multiple choice and free-form questions about these interactive syntax extensions. The second, the creation one, is more involved. It takes multiple hours. Because of this, we actually only ended up getting 1 participant who took part in this study, who actually spent multiple hours over the course of 1 or 2 months creating some pretty detailed interactive syntax extensions. We'll get to that part later. Let's first talk about the comprehension part of the first extension, or first examination. All right, so this, to tell if programmers could read code, we asked them a series of multiple choice questions. Each question had a visual and a textual variant. And because the only thing we had to get participants to participate in the study is we went to a bunch of ClojureScript programmers, went to various ClojureScript programming social places, and we asked them to participate, and the only draw they had was getting an early chance, or a chance to get an early peek at interactive syntax. So because of that, we needed to give everyone actual interactive syntax questions. So we split the participants into two groups, and we gave half the participants, we gave the participants in the first group the textual variant, participants in the second group the visual variant, and then for the next question we swapped it. All right. For the use aspect, we actually switched it up a bit and went to a freeform question. So this is a question from the second scenario. We provided them with a implementation of a 7-segment display editor and asked them to implement a 7-segment display that takes in a number and will display that number. And we provided them with the first segment here. These are the numbers to light up if the input value is that number. So 0, 2, 3, 5, 6, 7. Otherwise turn dark. And we asked them to fill in the rest of these to-do blocks. We also gave them a bunch of unit tests to see if it was, to test if their code was correct. The correct result is going to end up looking like this. And if we run it, it's going to print out into the REPL saying all tests pass. And we can even use this little example bar here to test different example configurations. So this is the 0 configuration. If we click plus, this is what the display will show if you press 1. And this is what it will show if you press 2. Okay, cool. So what did the results of this first study show? Well, interactive syntax actually did help participants read code. They got many more, they got more answers correct with interactive syntax than the group that did not have interactive syntax. Also, we found that more participants attempted the question with interactive syntax, whereas several of them that got the textual variant dropped out of the study. Before they got, or not dropped out, they skipped the question and went on to the next one. When it came to writing code, we found that more participants, participants were able to write the code. About 2/3 of the participants who tried to write code got completely correct code that used interactive syntax extensions. And finally, when we asked them to fill out their opinions on interactive syntax, they responded for the most part very warmly and wanted to be able to use interactive syntax in their code, provided that it ran in their preferred IDE and or language. The second experiment we ran, though, that one's kind of cool. So I want to give a shout out to Cameron Moy, who is our one participant. Now, this guy is amazing. He did not know anything about ClojureScript and very little about web development in general, actually. So thank you for reaching out and participating. And this is actually why it was done over the course of a few months rather than just, an intense weekend of programming. But he ended up making 3 separate editors. The first was a finite state machine editor. The second was an editor for visualizing data. And then the third one, which I think was kind of cool, is a way of programming PLT regex semantics using interactive syntax. It's that third one I want to talk about here, because it seems less interesting to some people, but I really find this fascinating that Cameron went here. Cameron essentially made a visual here. This is a simply typed lambda calculus with the following as its typing rules. If I can open it, there we go. And the following reduction code. Okay, so this is what a program in the lambda calculus that Cameron made looks like. In this case, it's just a function that takes an integer and then immediately returns that integer. Now, you may be thinking, why do I want this? Well, when my committee member, Robbie, presented PLT Redux almost a decade ago now, he showed that the goal of Redux was so that developers would able to run the type of models they put in papers. The thing is that the type of models developers put in papers is actual math notation like this. Before, when using Redux, it had to look something like this. This is honestly a best effort attempt to create the same program as above, now in just plain textual Redux. And it looks okay, but it clearly is not what you're going to give to a give in a paper. So in the spirit of trying to put the actual semantics you put in a paper in your code, we ideally want something like this. Now, question though, PLT Redux is in Racket. You can even see the hash length here. I thought Racket broke. So did we patch it back together and create this sort of Nightmare Before Christmas Frankenstein vibe? Actually, kind of, yes. So Cameron used this, essentially this bridge architecture I put together to run interactive syntax and bring it to languages that otherwise do not run right in the DOM. And the idea here is you have a front end that is your IDE and a back end that is your language server. The IDE sends the code to be executed to the language server, which then produces, a list of interactive syntax extensions, which it then sends back to the IDE to put in text. This is a lot like the architecture that we saw earlier. The big difference here is that this language server is not running right within the DOM, and it actually has to include with it the source locations that it should replace the interactive syntax extensions, because it doesn't actually know anything about the semantics of the language. So cool, this is good. Why is this a Nightmare Before Christmas patchwork? Why then did I go through this whole rigmarole of presenting ClojureScript when we can do this in Racket? Well, it's because this research hasn't gone entirely to its fullest extent. In particular, we need to think about what this little GUI reuse tab meant. Specifically, I mentioned it meant two separate things. It meant the engineering effort as well as sharing GUI code between the editors and the runtime. And while this Frankenstein's monster can make use of the engineering, the GUI sharing aspect is still forthcoming. So all of that doesn't matter though. Interactive syntax, all of this together, it is still usable, not just by me, but is shown to be readable and writable to many other people, and even extensible to people who don't know ClojureScript, but do have a clever head on them. So yes, actually, it is possible to create a useful and usable mechanism for programmatically adding visual and interactive domain-specific syntax to an existing textual programming language. I want to actually talk about future work because I have, I'm running out of time. Basically, the first direction that future work is going to go in is taking a look at pushing what we can express in visual syntax. Specifically, with the tree example, you notice that when we balanced it, we printed out a textual representation. It'd be nice if we printed out a visual representation of the tree that was balanced, as well as other things like, say, 3D visuals, which would be very helpful with, say, constructive solid geometry or parametric CAD tools. But remember that visual and interactive syntax is two things, and just as, even though it is not as flashy, it is just as important to talk about the interactive part of visual and interactive syntax. Namely, things like, say, the stepper is really great for helping people understand how their code or their macros are working. So it'd be nice if we could have a visual stepper, so to speak. Also, edit time makes sense, but what happens if you want special edit time code that runs only when you're in the middle of debugging your program? Maybe you want it to pop up your code and show you dynamic information where certain things are located in memory. So a sort of testing or debugging phase, that might make sense to continue exploring. And now I want to say thank you all for listening, and I will now take any questions if there are any. Thank you.
Hold on. Everybody, please unmute yourself and give it up for Leaf. An amazing presentation. So I will turn off recording.